Here we look at what's known as a KMap or a KMap. The KMap is a graphical method that's used to minimize, which when we say minimize, it's going to mean to simplify our Boolean expressions. So we've looked at using the Boolean algebra laws to simplify the Boolean expressions, but now we're going to use a graphical approach. And the KMap, the KMap, is a version of the truth table. So that means it can also be thought of as an abstract version of the Venn diagram. And we use this KMap to find the minimum sum of products expression. So the sum of products expressions are going to be known as prime implicants, and we want to find the simplified form of this. So remember what we have for a minterm. Minterms, a set of minterms added up, can represent a Boolean function. So for example, if I had A and I wanted to represent A as a sum of minterms, A would be written as A and B or A and B complement. And I've drawn the Venn diagram to the right just to show you. And B can be written as a sum of minterms. A and B is already a minterm. So in the minterms, you just want to have both elements of the set represented in each term, and you can have the complement of any of those elements. So here I'm just using that Venn diagram with a set A and a set B for an example. A or B can be represented as the sum of minterms. So I have its expression here as A and B, or A and B complement, or A complement and B. And again, when I'm writing these sum of products expression here, I am writing a complete sum of products expression at this moment, where I am including all of the elements that are in my set. So I have A and B here, so I'm including the A and the B, and then the A and B complements, etc. So that would be called like a complete sum of products expression. And one can be written also as a sum of products, a complete sum of products. So we have the two variable KMap, and this is where we look at 2 to the power 2, which means 4 minterms for 2 variables. So we're going to have 4 cells. So again, think of this as a truth table, just put a little differently. And the minterms of adjacent cells, if you notice, are going to differ by only 1 literal. And the reason is we've set up a gray code. So we've set up our gray code here. Now for the 2 variable KMap, I've written down my gray code to show you that if you want to call this, these are all the possible literals that can occur in a sum of products. So you know that this one here would be A complement, B complement. This cell would be A, B complement. This cell would be A complement B, and this cell would be A, B. So those are all the combinations that you can have for the 2 variable KMap, 4 of them. And then if you wanted to write it this way, that's fine as well. I've just, as you notice, I've switched this up here, and I put A and then A complement, and I could have switched down here as well. So what I end up with is I could call this B complement first if I want to, then A, B complement, then A complement, because I know I have that commutative property of multiplication, so it doesn't matter which one goes first. But those are, again, all the possible 2 variable combinations for my sum of products. Now here I've written it down a little differently, and this is standard, where we would put down 0s and 1s. So on this side, you write down the variable that it represents. So A can either take on 0, meaning A complement, or 1, meaning A. And then down here, I write down the variable. The variable is B. For the other of the two variables, and what can it take on? Well, B can take on 0, which is going to mean to us the complement, so not B, and then or 1, which means B. And again, on this side, I've written it for the way that you set up your cells according to your gray code here. So if you had a 1 in this position for A, then that would represent A itself. So notice that the edges would wrap around to form a torus or a donut shape, since those cells are adjacent to each other and they differ by only one literal. So what that means is you're able to take this side and this side over here, and you can tape them together and then tape this side with this side. So it forms this donut shape where your cells are going to be adjacent to each other. So just think about taping that together in each direction. And what that means is that if I looked at, maybe I'll take this one for example, notice how if you were to tape this side to this side, what would be those two cells? Well, this cell is B complement A complement, and then, so that's this cell. And then this cell down here is B A complement. And notice they do differ by just one literal. The only change was from B complement to B. So you can do that on each of them. So if you took, for example, taping, say, this side over to this side, so I'm just going to use these two cells, the B and A, how does that differ from B A complement? Well, in only one literal. So the Hamming distance there is 1 again. So I have B A and then B A complement differ by just one literal. So we have a 3-variable KMap that can be set up. So how many minterms will you have? How many possible minterms are you going to have? And again, with the minterms, that just means if you thought about your truth table, you know, how many possible combinations there, and it's 2 to the 3rd. So I have 8 cells. And one way to set this up is for 3 variables, you can put 2 of the products on top, and then you just leave one of the cells here, one of the variables for the row. And this is, again, a nice way to write it is using your gray code with 0s and 1s. So I'm going to represent that B and C are the variables on top here, and they can take on this 0, 0 means to complement each of those. So I'm going to do, this would be a B complement and a C complement. If you have 0, 1, that means B complement, but take C. Etc. And then here you write down the other variable. So we're going to write down A, and what can A be? A can either be A complement or A. So these are the same. I've just written them, one using the gray code with 0s and 1s, and one just leaving it with the literals. So either way you write it, what does it mean? So this is going to mean that this cell is the combination for that minterm. This cell is the combination for this minterm. You can call it a product. And you just go down the list there. If you notice here, so I decided to, let me just do these. So this is going to be an A complement, because if you notice that's a 0, so the 0 means A complement. And then the B has a 0 on it, so that's B complement, and the C has a 1, so that's C. Okay, this is going to be, again, A complement is coming from this 0. I'm going to write that one first. So it's going to be A complement. And then I have 1 and 1 here. So I have the 1 and 1, so that means take these variables as is, do not take its complement, just write BC. And the one under that, now I have 1 for the A, so that means I take A, okay, and then I still have B complement C, okay, again A, and then the 1, 1 up here, remember that means B, C, Okay, what happens, or do you notice if I just looked at those four together and I were to add up those products, what would you get back? So maybe we could look at it to the side here. So if I look at it to the side, just those four, we can use our rules, but what you have is you have A complement, B complement, C, and I'm going to add it to A complement, B, C. And let's just stop there for a minute. So that's going to be these two. So if I take these two, what do you get? So A complement and C are in common. So I can factor that out. And then you'll have a B complement plus a B. So any two adjacent cells, what's going to happen is when you add them, so when I say combine, I mean add, when I add them, you're going to eliminate one of the variables. Because what is B complement plus B? B complement plus B is just 1. See, that's a 1. So we end up with just two literals, A complement C. And now notice if I combine these two, see, the same thing should happen. I should eliminate one of the literals there. So if I add those two together, okay, what's in common is the AC, so I factor out AC. Then you have B complement plus B, which is 1. So we end up with A times C. Now if you add those two together, so I'm going to add this one and this one, what do you end up with? So A complement C plus AC, factor out the C, this is a 1, so you end up with C. So that's what I was writing here, is I was writing that if you take the cells in the middle, let me put my A back up here, you're going to end up with C, combining all of those. If you add them all up, you will get back C. And then I've located where you would get back A and where you would get back B. So verify to yourself that if you took the entire row down here, that entire row would give you back A. And you can see that, right? Because that's where you have the 1. The 1 means you have A's all the way across. Where would I get the B? The B will be these last two columns. Why do you have to sum up those last two columns to get B there? You have to take all of them, and that's where you had B as 1s. So here's the 1, and here's the 1, so that's taking on the B value. And you can, again, verify that for yourself, that you're going to get back B there. So this is the 4-variable KMap, so you have 16 cells because we have 2 to the 4th midterm choices here. So as I look at this, again, I've set up a gray code. So the gray code on top, 00011110. So we should remember that gray code there, 00011110. And then I repeated that down this side, 00011110. So why is it important? It is important to have a gray code. You must have your gray code in a KMap so that when you combine your cells, you will eliminate one of the literals. So that's how you're doing your simplification. And I've indicated where you're going to get back C, where you're going to get back your A, where you're going to get back your D, you're going to get back your B. So the B is 1 in those positions.